Alright, grade 10s, we're going to look at chemical change part 2. So going to some stuff that you've done before. We have actually revised this, we've done this. So this first part is actually nothing new. So remember that the relative atomic mass is of a substance is the mass of a particle on a scale where the atom of carbon-12 has a mass of 12. So it's a comparison, okay? It's relative. Relative means we compare it to something. We happen to compare it to carbon-12. It's a strange little comparison to do, but it's the one we do because we used to compare it to hydrogen, but of course hydrogen isn't as stable. Carbon is a far more stable compound for us, okay? So just to remind you how we do this, let's look at activity 1 on page 194. Grade 10s, you really need to be using your periodic table from the little booklet you were given because the one in your textbook has too many decimal places. So if we look at carbon dioxide, first of all, we want relative molar mass. So it's M with a little r. R means relative. Carbon has a relative atomic mass of 12. Oxygen is 16. There are 2 oxygens, so there's 44. There's no unit because it's relative. It's a scale. If we look at question 2, potassium bromide. Potassium has a mass of 32, relative mass of 39, not 32. Bromine is 80, so together it gives us 119. We're getting these values from the periodic table. Silver chloride. All right, next one, please remember every time we do MR first, we put in that in there so that we know which molecule we're looking at. It just is going to make life easier in the long run. And that's 108, which is silver, plus 35.5, which gives us 43.5. Number 4, calcium sulfate. Here we have calcium, which is 40, sulfur is 32, oxygen is 16. There's 4 oxygens, so we put it into our calculator and get 136. NH3, which is ammonia, it's one you're going to see often. Nitrogen is 14, hydrogen is 3, so it's 17. Then we get sodium carbonate, sodium being 23, carbon being 12, 16 for oxygen. All right, so when we put it all in, we get 106. Now, these relative masses don't help us very much because it's really more important to know how we can use it from a mass point of view, how to make actual use of it. So we're going to look at the concept of the mole. All right, now first we're going to look at Avogadro's number. Avogadro's number is very, very important. The atoms, molecules, ions, etc. are very, very small, so to count them in small values doesn't make any sense. So it's rather better to use large values because, of course, in any substance there's millions and millions and millions of these little particles, and you guys all know that they're very tiny. So in order to count them, we have to have a unit. We need a unit that's big enough, and that's what the mole is, okay? This unit is the mole. When we write it, we put MOL. That's the abbreviation for it, but that's the mole, okay? It's not a little furry blind animal that lives under the ground. The mole is given or was first proposed by an Italian physicist named Amedeo Avogadro. He was the son of a lawyer, and, well, I think he looks a little bit like a mole, but I'm sure that's not why they called it that, okay? So Avogadro's number is Na, N being number, A being Avogadro. Now, we define Avogadro's constant or Avogadro's number as the number of particles in 1 mole of a substance. So a mole is like a dozen. You know, if I talk about a dozen, that we have 12. If I have 3 dozen, you know it's 3 times 12. If I have a century, we have 100. So you know what those things mean. So a mole is a specific value or a specific number. So it's a way to group a certain number of numbers together. That number happens to be 6,02 times 10 to the 23. Now, the nice thing is this is given to you on your information sheet. You do not need to learn this one. So, we define 1 mole as being a substance that contains 6,02 times 10 to the 23 elementary units. What do we mean by an elementary unit? Well, that could be an atom, a mole, an ion, an electron. So for science purposes, elementary units are very, very, very tiny. We could theoretically count moles of people, but there aren't that many people on the planet. We could count moles of pencils or moles of chairs. It doesn't matter, but we count it in terms of elementary units. Very, very tiny, tiny units, okay? So this is the value. This is our definition. 1 mole is the amount of substance which has the same number of particles as there are atoms in 12 grams of carbon-12. So now we're not doing it as a comparison. We're giving it an actual value. For example, 1 mole of an element contains 6,02 times 10 to the 23 units. 1 mole of a compound contains, atoms, 6,02 times 10 to the 23 formula units. That just means, so something like NaCl, if I have a mole of sodium chloride, then we have 1 mole of sodium chloride units, okay? 1 mole of an atom, of an element or a compound, has a mass equivalent to its atomic mass or its formula mass. So now, if we take what we just did, all right, we can convert that into a molar mass, okay? So we'll get that in a second. Now here, just so you can see, each of these substances is 1 mole, but they all have a different mass. So 1 mole of carbon atoms is 12 grams. 1 mole of sulfur is 32 grams. 1 mole of mercury, which looks really small, is 200 grams. 1 mole of iron is 56 grams. Each of these substances, so these 4 things, represents 1 mole. That mole, okay, means that each of these things have 6,02 times 10 to the 23 atoms in them, okay? And it really doesn't matter that they're different, okay? It's really important. So that gets us to molar mass. Molar mass is the mass of 1 mole of a substance, and it's measured in grams per mole. Okay, so that actually makes life quite easy. So it's grams per mole. So 1 mole of matter always contains a definite number of particles, 6,023 times 10 to the 23. But they might have a different mass. So if I have 10 elephants and 10 feathers, I have 10 of those substances, but they have different masses. And that we can understand. That's not hard. So 1 mole of water contains exactly the same number of water molecules as there are sulfur atoms in 1 mole of sulfur, which happens to be the same number of carbon atoms in 12 grams of carbon. Okay, so let's look at some examples. What is the molar mass of magnesium? Well, we read it off the periodic table. It's equivalent to the relative atomic mass. Now, when I put the M, I do not put the R. Okay, so molar mass of magnesium is 24 grams per mole. The molar mass of H2O, I work it out the same way as I do the relative molar mass. All right, so it's mass H2O. Hydrogen is 1, oxygen is 16, so we get 18 grams per mole. Molar mass of sodium chloride, 23 plus 35.5, so it gives me 58.5. Very, very straightforward. Okay, so now what you need to do is you need to do activity 2 on page 195 before you move on to the next video.